Dear students, Assalamualaikum. Today we will discuss the second part of discrete circuit BJT amplifiers, which is a common emitter amplifier with an emitter resistance. We have already gone through the analysis of BJT amplifiers in a detailed way. Some of the main points are written here before going ahead. We have gone through the biasing schemes of BJT in desired mode, especially the active mode, because we were studying in detail the amplification using BJT. We have understood the basic BJT amplifier configurations, right? Now we have the knowledge of about the basic idea of discrete BJT amplifiers. We have performed AC analysis of a discrete BJT amplifier, the last one, common emitter amplifier, right? And especially the small signal models, hybrid pi model and T model. Let's analyze a common emitter amplifier with an emitter resistance. Recall the configurations of BJT based amplifiers. Common emitter amplifier, this one no emitter resistance, this one having an emitter resistance, right? This one actually we are going to study today. This one was studied in the last lecture. How about this one? We have discussed the name at least. This one is also called without RE, right? Because RE is bypassed for AC signal. This one will be your next assignment, right? So please concentrate. When you have understood this thing and when you are going to understand this thing in detail, then you can do this assignment easy, right? So now this one was the configuration common emitter amplifier we'll be discussing today, and the remaining two will be discussed in the upcoming lectures. Let's pose a practical problem by which we can make an understanding of the common emitter amplifier with an RE. Suppose you have given some of this amplifier already designed by someone and you are going to analyze it, right? So you have to draw the DC load line in the first part, find the Q point of the amplifier and locate it on the DC load line, right? Then draw the AC equivalent circuit and provide its parameters, GM, R pi, RE, R naught, right? Take these as constant, early effect voltage, VT, temperature dependent voltage, R signal, the non-linear sensing or the sourcing device is having a series resistance R signal of 10 kilo ohm, and load, your load to which your output will be loaded is of 5 kilo ohm. Then write the expression of voltage gains AV naught, AV, GV naught and GV did for the previous amplifier. Now we have to do it with this amplifier having an RE. Then we have to calculate the numerical values of these gains expressed in part D, right? What's new we will learn in this lecture? We will learn how to analyze common emitter amplifier, right? With an emitter resistance, right? Because with an emitter resistance, our computations for different voltage gains will be incorporating the T model, right? So it means T model will be applied here for the first time for your understanding, right? Draw the DC load line, the first two parts. Find the Q point of the amplifier located on the DC load line. We have done it while learning DC analysis. Please open that lectures and then you can see the same problem, because the DC circuit will be this one, right? Okay, we have introduced this nonlinear source later, but the DC signal, the DC equivalent circuit will be the same, and this one we have already analyzed we have drawn the DC load line, we have found the Q point and located on the DC load line while we were discussing this thing, right? So we are not going to discuss these things in detail, but a little exposure will be given while going towards the remaining steps, right? Okay, so the DC equivalent circuit would be, we already know that we have to open the capacitors to get the DC equivalent circuit, right? And we can now Thévenize this circuit at this point to have a simplified version, right? And Thévenizing at this point will be included with a VBB voltage calculation and the RB, the equivalent. So it would be, because when you will Thévenize, you have a parallel combination of these two resistances named as RBB, and at this point the voltage VBB will be the voltage across this. So R2 divided by R1 plus R2 into VCC, right? So for these values, it would be found to be 5 volt, VBB is 5 volt and 33.3 kilo written here already, right? So now DC analysis and Q point, I will abstractly present here. For detail, you can go to our previous lectures. So the Kirchhoff's equation about this L will be this one: VBB, IBRB, VBE, IERE, right? IBRB, IERE, right? And by using these relations of IC to IB and IC to IE, we can replace IE and IB by IC, right? And because we are working with an amplifier, so let's arrange it for IC, and because we are working for an amplifier, so VBE would be equal nearly 0.7, so we can put it here. VBE is selected to be 0.7 for an amplifier, and all other variables are already given to us, so we can find IC here, right? Now write an equation, Kirchhoff's equation about this loop. So VCC, ICRC, VCE, IERE, right? Now ICRC, IERE in the form of voltage, in the form of Ohm's law relations. By using this collector to emitter current relation, we can replace this emitter current with the collector. Right now, we already have IC. We can put here RC, RE, alpha, VCC already with us. So we can get VC is equal to 4 volts. So this is your Q point, right? So you can draw the load line yourself by finding the extreme points of the load lines, right? Input load line, input load line and output load lines, right? And place this Q point on that load line by yourself, right? So now we are going to work on the AC source.